Hi, this is problem 611. So we have a ball of clay that will hit a block which is attached to a string, which is further attached to another block, and that is connected to a stop, which prevents the large block from moving. As the ball of clay hits the small block, the block will certainly move in the direction that the ball is traveling towards. However, the spring will compress and then push back. To find the energy stored in the spring at the maximum compression, we can simply use our equation for potential energy in a spring, which is 1/2 kx squared, where x is the spring constant and x is the amount of distance the spring is compressed. The problem tells us that the spring constant is 200 newtons per meter and the maximum compression distance is 0.4 meters. Simply plugging these values in will give us a value of 10 joules, the unit for energy. Part B is the problem that deals with the conservation of energy. When energy is lost, energy is gained in some other system. As we can see, the clay ball will hit the small block and cause it to compress, giving it potential energy. The potential energy that was made is equal to the kinetic energy that was lost. So we can set 1/2 mv squared, which is the formula for kinetic energy, equal to the potential energy that we would have gained once the spring reaches the maximum compression. Because the ball of clay sticks onto the small block, the total mass is 2.1 kilograms. So, solving for velocity, we find that the velocity of the small block and the ball of clay is 3.9 meters per second. Part C wants us to find the initial speed of the clay. We can simply use the principle of the conservation of momentum. The momentum of the ball of clay before is equal to the total amount of momentum there is after in the new combined clay and block system. We have solved for the velocity of the new system in part B. And we also know the mass of the ball of clay by itself. Thus, we can set mv equals to mv and solve for the missing velocity. We see that there's less velocity as the momentum is transferred onto a bigger mass. This makes intuitive sense because if I were to run into a car, I would not move the car very much because the car is so much heavier than me. For part D, our removable stop is removed. We have to figure out whether the potential energy stored in the spring will be bigger or smaller or equal to than the amount of potential energy there is before. As the ball of clay hits a small block, the kinetic energy will again be converted into potential energy because the block is pushing on the spring. However, instead of having complete transformation from kinetic energy to potential energy, the ball of clay will also cause the big block to move. Thus, not all of the kinetic energy is converted into potential energy. The big block clearly has kinetic energy, and thus it is not a full transformation to potential energy. As a result, the amount of compression will be less than before because there's less potential energy, and the spring will not be as tightly compressed as a result. Problem E again deals with the concept of the conservation of energy. As we have seen before, the kinetic energy can be converted into potential energy and the other way around. The problem tells us that this spring regains its original length after being compressed. Thus, there is no potential energy we have to worry about. The total kinetic energy there is before is all there after. Thus, the equation can be written something like this. And simply plugging in our numbers, we can get something like this.